Okay. So we're we were doing this problem, and we came up with the result that the area under a curve is, well, I'm going to add up some rectangles in a summation. I'm going to count it from the first rectangle to the number of rectangles I have. I'm going to add their areas, meaning I'm only going to add up their height times their width. And let's review what this is. So this portion right here is saying, hey, we're adding up rectangles. I mean, areas of rectangles. And the way we come up with this is the formula for the area of the rectangle is base times height. Now, some people a lot are confused about this height right here and what it means. If we have some rectangle, and this is a curve, let's look at that one rectangle. Now that one rectangle has an x value, right? Now, let's say this was the second rectangle. Where would we put x up to? The x position of the second rectangle. Now, why not this one? Why can't we pick this one? Because it does not help us find the height of the curve. This one does because it actually hits the curve. See, if my next one's going to look like this, my next one's going to look like this, and that's going to be the third rectangle. This is going to be the height. This value right here is going to be the height of my second rectangle, my height of my third rectangle. And all these values here are delta x. The widths are delta x's, okay? And they're all the same. Now the area is base times height, right? That's what that is. It's saying, hey, we're going to count. We're going to plug in 1, and then we're going to plug in 2. And I want you to understand that this is how it works. So let's plug in some k values for this formula. At least for this one. So let's take this one. So what is, well, this is the limit as n approaches infinity of what? Let's just plug this in. Let's start at k equals 1. Well, if we plug in 1 into k, we get the height of the first rectangle times the width, plus plug in 2, the height of the second rectangle times the width, plus, well, we kind of know this is going on forever, right? Until we plug in n into the equation. We have the height of the last rectangle, n, times its width. Same thing as the other widths. And that's what it looks like. I need to understand that you know what this exact thing here equals that thing right there. And we talked about how we even got to that point from learning what the summation formula is. So, what the summation is. Now, I kind of rushed this part, this limit. And it's saying, well, we have an approximation if we don't include this. See, the reason why this is equal to the area is because if we had some curve and we had finite numbers of rectangles, we obviously have not found the exact area because we have some area missing. So if we want to find the exact area, well, let's take the limit. Let's find out what happens to this value as we let the number of rectangles get smaller. Well, obviously I'm having less pieces left over, so I'm getting more accurate with my answer. So obviously, or not obvious, but it kind of seems like if we let n approach infinity, then we're going to get an exact answer, because the more rectangles we have, the more accurate our answer will be. Well, how do we get exact? Well, we let the number of rectangles approach infinity. That's my whole spiel. Now we actually have to do some of the stuff. So, okay. Now before we learn how to actually evaluate this formula, we have to identify two things. This boy right here and this guy right here. We have no idea what that is. At least in the right form. So, what is delta x? What is our change of x? And I'm going to take this curve, for example, from A to B. Okay? So, we know we're going to divide our pieces equally, where each of them are delta x's, right? The width of each interval for the rectangles are equal width. Now, we're obviously choosing left or right endpoints for our rectangle. So this is what a right endpoint looks like. Right endpoint rectangle. Sorry, that was a bad one. This is what a left endpoint rectangle looks like. Now notice the difference. From the left endpoint, I'm making the left x value the height of reach the height of the rectangle. The right endpoint rectangle, I let the right endpoint reach the height of the function. So, specifically, how I'm going to zoom in to the endpoint, or the point itself. So if we are literally zooming in from the A's and the B's, and we have equal distance intervals where our rectangle is going to be, this is the x-axis. What is this value here? Well, let's pretend I had three rectangles, right? And this started at A, and the other one started at B. What is the width of each side? Well, aren't we dividing the entire thing into equal sections? How many sections are we dividing it to? To the number of rectangles, right? So if n's the number of rectangles, well, what's the distance of this segment? It's b minus a, right? And we're dividing it into equal pieces, but how are we dividing it? To the number of rectangles, right? That's how we divide. So that is the definition of delta x. Okay, let's cover the harder one, which is this one. This one is difficult because there's 3 different ways to do it. 3. If we're using right endpoint, so this could be multiple things. So if we're using right endpoint, what is it going to be? Because this takes the x position of the rectangle and plugs it into the function. Well, if we're having all x positions of the rectangle being the right endpoint, what is the formula of every right endpoint? Well, it's the first one's A. So let's jot that down. The next one is what? A plus the delta x, right? The next one is what? A plus delta x plus another delta x, right? And the next one is again A plus delta x plus delta x plus delta x. So what I'm really doing is for every rectangle I'm skipping, we're adding or multiplying that by delta x. But we're going from k equals 1 to 1, right? So the first one, see the one, ooh, See the first one is just going to be the A. Well, that's the left endpoint, right? Right? Sorry, that's the left endpoint. Let's cover the left endpoint then. So this is A plus 0 delta x. This is A plus delta x. A plus 2 delta x. So I'm going to get this A value when we have the first rectangle, the second rectangle, the third rectangle. So what's happening to my k's in relationship to this number right here? Well, we're subtracting 1 from k. So the formula for the right endpoint, or the left endpoint, sorry, is A plus k minus 1 times delta x. So it's the number of the rectangle you're doing minus 1 times your delta x plus your A. Now for the right one, it's more easier. Your right endpoint so this is the right endpoint. What's A plus delta x? This is the first rectangle, right? This is the right endpoint of the second rectangle. Ooh, we already see a pattern. There's 1, 2. So the right endpoint formula is just A plus the number of the rectangle you're on times delta x. There is the last one called the midpoint. And we're not going to cover that one because it's just too... It's just a nastier one. We don't want to use it. We literally always want to use right endpoints right now. We're not going to use even the right left one. Because look at this formula. Which one do you prefer? Well, I prefer this one because that doesn't have the k minus 1. That just has the k. So that's why I don't want to really do that. So that's x sub k. That's their x position. As soon as we take the function height, well, we have to take the f of both of these. The f of that. The f of the x value. So now we have all the pieces we really need. So let's solve an area problem for the first time. I'm going to choose the most classic one. The most classic example. Okay, we're trying to find the area under y equals x squared from 0 to 2. Okay. And visually, it looks like this. That's what it looks like. That's the area. Okay. Let's do it. So we need two pieces. We need the delta x and the f of x sub k? Well, it's delta x. Well, that's just b minus a over n. Well, how many rectangles are we using? Well, we're going to use infinitely many, but we're just going to say n for now. So what's b minus a? What's 2 minus... Oh, this is from a to b, right? From a to b. Well, b minus a is just 2 over n, right? What's our x sub k? We want to kind of use the right endpoint because it's so simpler. So this is a plus k delta x, right? That's the formula for the right endpoint of every interval. Every sub-interval, sorry. So this one is going to be the a, which is the 0, plus k, which is legit k, and the x. Okay. You got that one? We have everything we need. We can plug it all into the formula. So I'm going to erase this. Just remember this is delta x is 2 over n. X sub k is... Ooh, wait. What is f of x sub k? We'll find out later. So that's just... That's x sub k is just k times delta x. And delta x is 2 over n. Just remember that. I erase this because we need a lot of them. So we're gonna do this. So this area is equal to what? We have to put the limit there, so that's the limit as n approaches infinity of the summation from k equals 1 to n of f of, wait, what was our a? What's the x of k? Well, it was just k times our delta x, right? Times delta x, which is just 2 over... Wait. Well, delta x is just 2 over n, so this is just 2k over n, right? That's it. That's our formula. That's for the area under the curve of the x squared from 0 to 2. That's the area formula. How do we do it? Okay, well, let's think about summations, what they really do. Summations take... Ooh. So what is this variable? K, right? Okay. Let's take f of 2k minus over n. Sorry. So we still have a sum from k equals 1 to n. What is f of 2k over n? Well, it's the square, right, function? So it's 2k over n squared times 2 over n. We can clean that up a little bit. It's the limit as n approaches infinity of k equals 1 to n of 4k squared over n squared times 2n. So I'm going to put an 8 here. I'm just combining these. Times n to the third. Okay. So we have a variable k here. I know for a fact that we're going to plug in 1 in this case, right? First, right? Now, because we don't have anything affecting this n, we can just pull it out. Because no matter what number I'm going to put in here, we're in effect going to have still n to the third. Because we're not going to plug in a 1 to n, we're plugging a number into k. So this is the limit as n approaches infinity of 1 over n to the third of the summation from k equals 1 to n of what? Well, we can pull out constants too, remember? The 8? The 8 doesn't matter, it's not going to change. The only thing that's changing is the k squared. Ooh, do we have a summation formula for this? We do. Remember the k squared one? From the problems we did? The k squared one. We know that one. I'm going to move over here. This is what? The limit as n approaches infinity. Well, we know this is still there. This a over n to the third. Now this is multiplied by this entire summation, which we know the formula of, right? It's n times n plus 1 times 2n plus 1 over 6. Okay, well, we have that, okay? Now, if I were me, I would just do it right now, this limit. But for you, it's kind of hard to know this. So if we kind of simplify this a little bit, this is 8n times n plus 1 times 2n plus 1 over 6n to the third. Now, from here on out, that we have to find as the n approaches infinity. Wait, this looks like the rational function, kind of, right? If we expand all this stuff on top here, we're going to get what, 8n squared plus 8n times 2n plus 1. Well, what is that going to be? That's going to be 8 over 16n, sorry. So 8n squared times 2n. That's going to be 16n to the third. And then 8n sorry. n squared, 16n, and then what? 8n squared times 1, 8n squared. The next one's going to be 8n times 2n, which is going to be 16n squared. The next one is going to be 8n times 1, 8n. This is all over 16n to the third. Hey! Remember I divided 1 over n, or 1 over x on both sides? Well, remember, this is a rational function. We know the shortcut here to the limit as n approaches infinity. We know, well, if we have the same degree on top and bottom, our answer as n approaches infinity is going to be 16 over 6. So this equals 16 over 6. And if we divide both sides by 2, it's 8 over 3. That is the area under the curve. That right there is the area. This is what this is. This is literally x squared. This is x squared, right? This is your x squared function, right? And we're taking it from 0 to 2 and finding this area under it. We're finding this area under it. That is, this area here is 8/3. Hopefully, sorry. Now that right there is some cool stuff. Now the issue here is this is the easiest it's gonna get. There are some problems where it ain't as easy at all. So if, let's say we had x squared plus 2x plus 1. And I'll just randomly put that here. So, and we still went from 0 to 2, so we still had kind of the same form. Right? We still had from 0 to 2, and we still had right and formula. Right? Except our formula or f of, would be that plus 2k to the n plus 1, and then that would be delta x, right? That'll be 2 over n, right? So if we had the function x squared plus x plus 1, if we plug in 2k over n for that function, it would look like that. Now from here on out, you're gonna have to again clean this up again. This is the summation from k equals 1 to n. Okay, it's gonna be 4k squared over n squared plus 2k over n plus 1 over 2n. You're gonna have to distribute your n, so you're gonna have 8k. You don't have to distribute, but I honestly can. I like to do that. To the third squared. That's going to be a 4. That's going to be 2 over n. And this is what you have left. Now, you have addition. Last time you had multiplication. You're going to have to make this a 3 summation thing. So you're going to have to find the limit as n approaches infinity of the summation from k equals 1 to n of 8k squared over n to the third plus the summation from k equals 1 to n 4k over n squared plus the summation from k equals 1 to n of 2 over n. So you're going to have to evaluate each of these individually. Now, I already did an example where you evaluate this kind of thing. It's all going to be just things and n's. It's going to be a rational function. You're going to have to take the limit of each rational function here. It's not that hard, it takes a long time, and I can't even show this on the board unless I'm going to do it really small. So, you're going to have to do that. But you already know how to do it. We know how to do the summation right here. I've showed you it. You pull each of the n's out, and the constants. We're going to have a k squared summation formula. We have a k formula for summation. And this is just as a 1. That's just going to be n times 1. So we just have all of that summation formulas. It's all going to be in the form of rational functions, so that we have the n approach infinity of each of those rational functions. And you're going to have an answer of a constant. And that's how these area problems are going to go. So I encourage you to actually finish this problem. So remember, this problem is saying f of x equals x squared plus x plus 1. And I have the interval from 0 to 2. And I'm trying to find the area. Give me the area, please. That's what I want you to do. I want you to finish this problem. That'll be your kind of problem to do.